This is Math Studies Lesson 9.2, Geometric Sequences. So a geometric sequence is, again, a list of numbers. But this list of numbers, unlike the arithmetic sequences, they will change by a common ratio. And what that means is rather than adding or subtracting values to get the next and the next and the next, we will be multiplying to get the next and the next and the next and the next. So I think doubling is usually an easy one that people know. So if we're starting with 2 times 2 is 4, times 2 is 8, times 2 is 16, 32, 64, 128, 256, 512, 1028, so on and so on and so on and so on. If we're unsure of what the ratio is, it can be calculated by taking the second number in the list of numbers and dividing it by the first number in the list of numbers. So that's like we multiply to move forward, so we would divide to move backwards. Second number divided by first number. I have two more ways, really one more way, but two styles, to calculate a common ratio, and that's when you're given a percent increase or a percent decrease. So a percent growth, percent increase style situation, if you need to calculate your ratio, you would need to do 100% plus whatever percent you're given. So a quick example of that would be if I wanted to do a 12% increase. To calculate my ratio, I would need 100% plus 12%. That is 112%. Now, percents, we need to remember that we want to move the decimal 2 spaces to turn it into a decimal. And so my actual ratio in this case would be 1.12. A percent decrease looks very similar, but instead of adding to our original 100% that we start with, we will be subtracting from our original 100% that we start with. So if you're told to do a, for example, 8% decrease, we would start with 100% and then remove 8% from that. That leaves us with 92%. We need to decimal 2 spaces, and 0.92 would be the ratio for that case. So 3 different ways to calculate ratio. If you have a list of numbers, we need to divide to figure out how to move forward. If you have a percent increase, add that percentage to 100%. If you have a percent decrease, subtract that percentage from 100%. Our recursive formula is going to look very similar to the recursive formula from the arithmetic sequences. We're given a starting number, and then off of that starting number, we are told to repeatedly multiply by a ratio. The explicit formula, if we want to jump right to a specific answer rather than generate a list of answers, we're going to start with the 0 number, just like the arithmetic version, but I'm then going to multiply it by whatever the ratio is. And if we want to repeatedly multiply something, we raise it to a power. The ratio calculation is given 3 different ways up top. The 0, though, if we need to figure that one out or we're not sure, remember, you can always take your first number and divide it by the ratio. Multiply to move forward. Divide to move backward. So with those examples, with those notes, let's try some examples. The first one says, consider the recursive formula u sub 0 equals 2.5, u sub n equals u sub n minus 1 times 2. Use it to find the first 4 terms in the sequence. So we're given the starting number. We're told how to get the next number and the next number and the next number. Recursively, I think it makes the most sense to go to the calculator because I'm going to put in my starting value, and I'm going to hit enter. I'm going to hit times because recall that this looks like answer on my calculator. So when I hit times, the answer piece pops up all by itself. So times 2. Starting value times 2, answer 1, answer 2, answer 3, answer 4. And that's the point of seeding it in 2 steps like that. We can jump right to the next and the next and the next just by hitting enter without having to type anything additional in there. So U sub 1 is 5. U sub 2 is 10. U3 is 20. And U4 is 40. Now this specific example, I don't know if we necessarily needed our calculator. We're just doubling. It's not hard to double, but it's a good tool for when we're multiplying by more complicated ratios. I don't think we can generally multiply by 0.72 in our heads. Probably can't multiply by 3.7 in our heads that quickly, but use that tool with the enter, enter, enter style when you get the more complicated ratios. And now we want an explicit formula. I'm going to put this back up just a smidge so I can see this is our goal for the explicit formula. So we need 2 things, the 0 number and the ratio. We're already given the 0 number, and we have our ratio right here. So our explicit formula looks like U sub n equals, our 0 number was 2.5, and our ratio was 2, and we'll raise that to the power of n. And just to show how that would work, maybe if I wanted the 4th answer without having to get answer 1, answer 2, answer 3, and answer along the way, we can put in 2.5 times 2 raised to the power of, that is called a caret, it's a little upwards arrow, raised to the power of 4 is giving me the same answer as 4 enters did. Let's go on to example B. I'm given an explicit formula now. If I want to find the first 4 answers using an explicit formula, that's a little more work. Using the explicit formula, I'd have to go that times that to the power of 1. And then I would have the exact same thing, but to the power of 2. And then the exact same thing, but to the power of 3, which isn't difficult. It's just a little more typing than the recursive method. So I have answer 1, answer 2, answer 3, answer 4. Let's see if I can remember these. 192, 48, I already forgot. 12 and 3. I'm going to come back and label them now. The first answer was, the second answer was, the third answer was, and the 4th answer was. Now, knowing what I know, that this is the 0 number, and that this is the ratio, I'm going to write my recursive formula if I was going to do this enter, 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 enter style instead of power 1, power 2, power 3, power 4 style. I know the 0 number is 768, and to get the next answer, I take the answer, previous answer, and I multiply by 0.25. So if I had done that method instead, 768 times 0.25, answer 1, answer 2, answer 3, answer 4, it's a lot less typing to get to the same list of values. So I like the recursive formula when I need a list of numbers. I like the explicit formula when I want to jump right to a specific answer. And it looks like I have more examples on the next page. So example C, we have a list of numbers, 2, 6, 18, 54. Write a recursive formula, write an explicit formula, and then find the 18th term. We need 2 things for a recursive formula. We need the 0 number and we need to get the next answer. We take the one before it, and I know that this is geometric, so we're going to multiply by something. Let's figure out our somethings. The ratio from a list of numbers can be figured out by taking the second number and dividing it by the first number. So I'm going to take 6 divided by 2. I know that this is multiplying by 3 to get the next, and the next, and the next. And just in case I don't trust that math, I'm going to try it out. 2 times 3. 1, 2, 3. And I got 6 and 18 and 54. Definitely matches up with what I was given. So I like that. My ratio is 3. I know the first number is 2. The second number is 6. The third number is 18, but I'm looking for the 0 number. So to get the 0 number, we need to take the first number and divide by the ratio. I had all these formulas on the top of the front page, but I'm putting them here too, just so that we know what we're working with. So I know the first number is 2. If I divide it by 3, right, times by 3 to move forward, I can divide by 3 to move backward. That's a decimal. I'm going to leave it in fraction form. I'm going to keep it 2/3. We could write 0.6 repeating, 0.66666, but I'm going to keep 2/3. And I'm doing that specifically because I don't want to get rounded answers if I round that decimal. Like if I go 0.66 times 3 to the power of 4, I should see 54 because I know my fourth answer is 54. But when I do that, I'm going to get 53.46. It rounded it down because I didn't use 2/3 proper. If I use the actual 2/3, rather than rounding 2/3 to a decimal, I'm going to get the exact answer I'm looking for. So my explicit formula then, I need the two pieces I just put into my recursive formula. It'll be 2/3 times 3 raised to the power of n. And finding the 18th term then, I just need to substitute 18 in for the power of n. So I will go 2/3 times 3 to the power of 18. That looks good. That's a big number. 258,280,326. Let's see. 258,280. Nope. 326. I thought I could remember it. So that looks like if we kept going 2, 6, 18, 54, and so on, and so on, and so on 18 times, we would end up with 258,280,326. It's getting to be a long video, but we're going to keep going. We have a word problem left in our example set. It says, an automobile originally costs $14,000 and loses 20% of its value every year. Write a recursive formula that represents the car's value after every year. Recursive formula, I need the 0 number, and I need the ratio. To calculate a ratio with a percent decrease, we're going to start with 100%. Take away 20%. That leaves me with 80%, but we're going to decimal, boom, boom, 0.8 or 0.80 are the same thing. So we have our 0 number given right there, and that looks like a complete recursive formula. 0 number, 14,000. To get the next number, I take the answer and multiply by 0.8. I can plug both of those values into my explicit formula, which is helpful for jumping right to whatever answer I'm looking for. What is the car's value after 3.5 years? I'm going to substitute that value in for n, 14,000 times 0.8 to the power of 3.5. Did I freeze? There we go. After 3.5 years, the car will be worth approximately $6,411.25. When is the car's value less than 3,000? This is a case where I feel the recursive formula is actually more helpful than the explicit formula. I'm trying to get my first value under 3,000, so I can go off of 14,000, my starting value, and then multiply it by 0.8, and I'm going to count how long it takes me to get to 3,000. So that's 1 year, 2 years, 3 years, 4 years, 5 years, 6 years, 7 years, 7 years. 7 years and the car dips below 3,000. if we wanted to go with a guess and check model instead of a recursive model, we would be trying different numbers for the power until we reach our goal answer. So I might try 5 to start off with. That's not low enough. I might try 10 next. Oh, that went too far. And trying different values in for my power until eventually I try 7. And that should be, missed a 0. The value closest to 3,000. We will be discussing later in this packet how to solve an exponential situation. I might be wrong about that. Oh, we did that in chapter 8. So we could use logarithms to do that. Either way, we have a recursive way, we have a logarithm way, we have a guess and check way. Lots of different ways to try to solve that one. That's it for these notes. Good luck on the exercises, and please let me know if you have any questions.